So this is the first of a series of videos trying to go over the paper by Link et al. And what I want to do is begin with a review of generalized linear models, in particular logistic regression. And what I want to do is I want to think about how we could simulate some data that would be appropriate for analysis by logistic regression. And we don't actually have to do the simulation. All we got to think about is how we might be able to do the simulation. And what we want to do is consider the process that gave rise to data that might be evaluated by logistic regression. Because if we have a clear understanding of the underlying process that gave rise to the data, then we have an understanding of how our logistic regression actually works to analyze those data. So the example I'm going to use is the one we saw earlier, where we're looking at the effect of age on whether or not folks liked classical music. And so we can consider initially these four individuals, their ages, 18, 20, 25, and 35. And our model, we're going to have a linear model that says that the ln of p over 1 minus p is going to be equal to minus 4.3 plus 1.4 times the age. And we can think of this thing here as being the logit, and this p is the probability that that person would like classical music. So we can use this formula and come up with ln p over 1 minus p for those four individuals. And if we did that, we would get values like minus 1.8, minus 1.5, minus 0.8, and 0.6. Of course, what we're really interested in is the probability, not the logit. So somehow we need to be able to extract that probability from the logit, and we can think about how we might do that for this particular individual here with a value of minus 1.8. What we would do is we take e to the minus 1.8, 1 plus e to the minus 1.8, and that would give us the thing we're interested in, the probability as being 0.14, and we can continue that with the rest of the people and get 0.18, 0.31, and 0.65. Now, while we're thinking about this, we can see the advantage of using a logit as the dependent variable of our linear function. And the reason is that when we back transform using this, we get a very desirable result, so that if this thing is minus infinity, then the value of p is going to be 0, whereas if this thing is plus infinity, the value of p is going to be 1. And so we're going to wind up with p values that go between 0 and 1, regardless of what the output is of our linear function. So we've got these p values, but now, fair enough, we know that the probability of this individual liking classical music is 0.14. But when we poll that individual, do they like classical music or do they not like classical music? And the whole idea is what we're going to do is we're going to determine this y value, whether or not they like classical music, which is going to be a 1 or a 0, 1 if they like classical music, 0 if they do not. and it's going to be drawn from a Bernoulli distribution that's got, there's a 0 and 0.86, and there's our 1, and it's 0.14, and we extract a value as a random sample from that, and we get a bunch of zeros and ones. Okay, so now we thought about the process that gave rise to those 0 and 1s, we can now see the three components of a generalized linear model. So there was our linear predictor, alpha plus beta x, minus 4.3 plus 1.4 times the age, and it predicted, without any variability, the link function, which was the logit. Once we got the value of the logit, we had to back transform, and that gave us p. But then we had to go from these probabilities to some zeros and ones. And we did that by taking a single observation from a Bernoulli distribution with this parameter p. And when I went over generalized linear models earlier, remember I said something about this idea, this distributional mechanism for obtaining the observed values was really kind of a Copernican revolution relative to what you would have seen in a lot of your other courses. In a lot of other your courses, what you would have had was a linear function, and then you would have added to it some residual. And that's how variability would have been introduced, by tacking on a residual to your expected value. But that's not what we do in general linearized models. In general linearized models, how we obtain variability is to randomly obtain an observation from some sort of a distribution which has a particular parameter. So with that review, now what I want to go to is to think about the study that Link et al. Did. And they examined, in their study, they had 845 individual birds. And these birds entered the study at various years. So there's a cohort that entered in year 1, another cohort that entered in year 2, another cohort that entered in year 3. If you add all these up, you get 845 birds. But what we're going to be interested in right now is whether or not these birds bred. Did they bred? So if they entered in this year, well, they'd have breeding events between year 1 and 2, and then breeding in year 3 and breeding 4. So you've got many breeding events, but you've got a lot of birds, and each one of those birds was tracked over a really long period of time. So in terms of the variables, these are our independent variables, the age of the bird, and what happened was that each chick was marked, so they knew the exact age of each bird. The year was the calendar year, and then each one of these birds, each one of these 845 birds had a unique identifier. And the dependent variable, normally we call the dependent variable y. Just to be consistent with Link et al., I'm going to call the dependent variable b, but just as with the case with y, you get a 1 or a 0, a 1 if the bird successfully bred, a 0 if it did not successfully breed in any particular year. And so here's going to be our model. And what we've got here is the logit. And what we're interested in is theta b. So theta b would be the parameter of a Bernoulli distribution from which either a 1 or a 0 was drawn. And so here's the model here. And in one font we have the coefficients. And in another font, we have the variables in our data frame. So this first thing is just the intercept, the age of the bird, the calendar year, and then the ID number of the bird. So that's going to be the model that we're going to come up with. And then these are the various coefficients. The coefficient that I really want to focus on now is this one, because this is going to be really important in terms of interpretation. So what is alpha beta? Alpha beta we can think of as being the breeding ability of the bird. And it's what we can think of as being a latent variable. Something that we think exists, but we don't know exactly how to measure it. We can't see it directly. A good example would be, batting ability that we saw in our baseball example, or scoring ability that we saw, or that we can think about if we consider the NHL. So here's a bunch of goal scorers. So here's the name of the scorer. There's the team. There's the rank. There's the number of goals. And we might be interested in this, if you figure out how much to pay him or whether or not to trade him, the ability of the individual to score. And that's really what we're interested in, but we can't really measure it directly. I mean, you can think, well, sure you can. Sure you can. You can just see how many goals they scored, and that is a measure of scoring ability. Well, it may be an index of scoring ability, but it's not really what we're after. What we're really after is some sort of a latent thing that we can't really get our hands on, that we can't measure directly, which is the ability to score goals. And one way to think about it is, if you think about these two players here, Ovechkin and this guy that I've never heard of, looking at the number of goals scored, you would say that Ovechkin is better than this dude. On the other hand, at the time that I got these data, Washington had got 61 points, Chicago had got 41 points. So it seems to me quite possible that this dude's scoring ability is better than Ovechkin's, and he actually would have had a lot more goals if he played for a more decent team. So anyways, this is just a brief introductory video, kind of sets the stage for other videos that are going to continue to get us our heads around this paper by Link et al.